What's up, guys? This is Jay Does Math. If I asked you what the point of linear algebra was, you might tell me it's about matrices and doing different operations on them, like multiplication or finding the determinant. But I would tell you that that's not the real point of it. Those are useful, but it's not kind of the actual idea behind it. And this video, I'm going to be going into the actual idea of what linear algebra is about. So, linear algebra, the actual idea of it is about vector spaces and transforming vectors from one vector space onto another. So what we have here is a vector space. This is R2, which just means all of the vectors in it just have two numbers associated with them. Like, for example, 2, 1 will look like this. 2 to the right and 1 up. So this is a vector in R2. So if we have this vector, you can see that it's 2 to the right and then 1 up. So if we wanted to find a way to represent this vector in its most fundamental parts, we could say it's a combination of moving two movements to the right and one up. So this plus this makes the vector 2, 1. So we can say it's the combination of these two vectors. If we wanted to break this down even more, we could say that it's equal to this plus this vector plus this vector. That's the same as saying it's equal to this. So all this means is that the vector 2, 1, this one, that's diagonal, is equal to 2 times 1 to the right, these two, plus 0, 1. This can work for any vector we choose in R2. So let's say we have a vector like this. It would be 4 to the right and 1 up. If we have a vector like this, it could be 2 to the left and 1 up. And we can have a vector like this, and it'll be 1 to the right and 2 down. Let's do this example again. So this vector is equal to 1 to the right and 2 down. So it can be written as this. Right? Yeah. As you can see, there's always these two parts of the vectors that always stay the same, 1, 0 and 0, 1. In R2, this is the standard basis. So we usually refer to this one as E1 and this one as E2. Sorry, I made these weird diagonal lines. I don't need these. Okay, so these two vectors are the standard basis. A basis doesn't have to be the standard basis, but this is like the most general one. So for this video, this is what I'm going to be using. So as I've shown, any vector can be represented as the standard, as like a linear combination of the standard basis. I can even do a weird vector like something like this that's not exactly at a point, and it, for example, this one would be negative 0.5 1.5, and it would just be equal to, this time I'm going to be using e, negative 0.5 times e1 plus 1.5 times e2, where e1 is this vector and e2 is this vector. So I hope that makes sense. This is the main idea of what a basis is. So we have that checked off. A basis also has to, it has to span the vector space, and that means, as I've shown, that any vector in this, like how I was showing before with this, you can choose any vector in here. And just with E1 and E2, some combination of them is going to be able to equal to it. Yep, so it spans it, and they're also linearly independent. And that just means that no matter how much you multiply this vector by a constant, it's never going to equal to this vector. I'll go into more detail about that in a later video, but just to be a little specific with it. So now I'm going to explain more about linear maps. So all linear map is doing is mapping one vector space to another. Usually you would do it like from L of maps V1 to V2, something like that. This looks like fancy and confusing, but it doesn't have to be crazy. Let's say we're mapping, we can map a vector space onto the same vector space, but just shift the vectors in that vector space. That's what it usually does. It just is like a shift of the vectors in the vector space. So for example, we can have a vector 1, 1. Again, we're in R2. R2 because there's two real numbers, 1 and 1. Or just any two real numbers could be in R2. So this vector 1, 1 is in R2. Let's say that the linear map we want to do, again, a linear map is just some like movement of the vector in R2. So let's say this linear map, we want to stretch it to the right 3 for every one movement this vector is to the right, we stretch it to the right 3. And for every one movement this vector is up 1, we stretch it up twice. So if we did a linear map from this vector, it would go here. Because as you can see, this vector's basis is going to be equal to E1 plus E2, 1 times 1. So it's going to be stretched from moving 1 to the right to moving 3 to the right, and it moves 1 up, and it's going to be stretched moving up to moving 2 up. So that's what this linear map does. I'll do another example. Let's say that we start with the vector -1, 2. It would be equal to -1 E1 plus 2 E2. So if we applied this same linear map to this vector, again, the linear map just stretches it however we defined it, and we defined it to multiply its left movement times 3 and its up movement times 2. So this one, it would move to the left 3, so it moves currently 1, so it would move 3 total to the left. And then its up movement would be times 2. So it would move to here. Okay. We can kind of like, not very like formally, but just say this vector does times 2 left and right stretch, and then, oh wait, no, times 3, sorry, and then times 2 up and down stretch. So this one gets mapped to here. So basically, we're saying that this linear map will map the vector 1, 1, this one, to the vector 3, 2. And it maps the vector -1, 2 to the vector -3, 4. Like, this is just represents you're doing a mapping of this vector onto another vector, and how we defined it by extending it 3 to the left and right, and then 2 up and down, based on whatever it kind of started as. So we can describe this this linear map more formally as a modification of its basis. So for example, we can say that the linear map from the vector 1, 0, since we defined it as moving 3 times to the right, it's going to be equal to 3, 0. And then the linear map of the vector 0, 1 is going to be equal to 0, 2. So this is the definition of the linear map. This is how we're defining it more formally. And then when we plug in these arbitrary vectors here, like 1, 1, we're just breaking these vectors down into its components, which are 1, 0, and 1, 1. And then we can do the operation of the linear map on those little components. So for example, the vector 1, 1 is split up into 1 to the right and 1 up. And then 1 to the right gets transformed to 3 to the right, and then 1 up gets transformed to 1 up gets transformed to 2 up, as you can see here. And then you combine those two, and you get 3, 2. Same can be done here. You can do this one yourself, but you can see that it'll get transformed to negative 3, 4 if you break this one down into a linear combination of its basis vectors. Actually, I'll do that right here. It'll get broken down like this, as I wrote above. And I'll go into more detail about this later, but this can be broken down further into this. And this can be broken down into this. And this really just shows that it's all based on how the linear map is defined for the basis vectors. Again, this is E1 and this is E2. It's the same as this. I could have written this as E1 and could have written this as LB2. And then this will be negative 1 times 3, 0. And then this will be plus 2 of 0, 2. And then again, you get the vector negative 3, 2. Oh, 4. My bad. And bringing this back to what a matrix is just a representation of this linear map. All a matrix is doing is showing what this linear map is doing. Since this is R2, this is mapping R2 onto R2. I should have written this before. All it's doing, it's gonna be it's gonna be a 2 by 2 matrix. This column of the matrix corresponds to the first basis vector, and this one corresponds to the second basis vector. It corresponds to the output of what happens when you do the linear map on this vector. So when you do the linear map on E1, you get 3, 0 right here. So this side is going to be 3, 0. And when you do the linear map on this basis vector, you get 0, 2. So this one is going to be 0, 2. So what I'm just trying to show you is that linear algebra is about applying linear maps to vector spaces. And this can be used to like represent the linear maps as matrices, but that's not the whole point of linear algebra. The whole point is linear maps, vector spaces, and all the properties and stuff that comes on after that by just making more statements and more operations and different things on from that. But that's the real kind of fundamental of it. So thank you for watching.